So next, Rob Levy from NASA is going to provide an introduction to the satellite data for air quality applications. We also have some nice game here to kind of get you all stand up and interact. So turn it over to Rob.
Where is it? Hold on. Just go. All right. Thank you, everybody. So my name is Rob Levy, and I'm from NASA Goddard in Maryland. I happen to be working on satellite remote sensing of aerosols, which are the our name for the particles in the entire atmosphere. I've been at Goddard for about it's been 20 years, and mostly working on this same project in its many different forms. So I'm talking about application of satellite data for air quality. And again, I'm talking about aerosols. So what's interesting is that there's many different kinds. So, and you can kind of see them by their color and how they look relative to the ground. So our work is trying to use the satellites to try and estimate and quantify the amount, loading, and type and properties of these particles. So I'll move on. Let's do this right. So what we often work in is a fundamental physical quantity called aerosol optical depth. How do I get this thing to get rid of in the middle? Oh, it's gone. Okay. And what optical depth represents is it's not actually the number or the volume or anything that's really easily physical, but it expresses the quantity of light removed from a beam by both scattering and absorption during its path. And so this is what we call, and the portion that's due to aerosols in the atmosphere is called aerosol optical depth. And these pictures over here kind of give you a sense of what we mean by visibly, if you see an optical depth of 0.4, where you can kind of see through and you can see the surface, but visibility in haze, it's definitely obvious. And an optical depth of 2 is like you can't see much at all. And another property is that optical depth depends on wavelength, and it's also related to the properties itself. So like the size and the shape and the composition of these particles. And so, our job is to try and use satellites to figure out those properties, the little particles in the middle, in relation to everything else that's both at the surface and the atmosphere. And just to mention, we do have a ground truth, which is basically what we call a sun photometer, which is at the ground. And so it's measuring directly the amount of light that's being removed. And so that's kind of our ground truth. So anyways, a little bit about how we do it. We can obviously see this from space. So here's a beautiful picture of extreme haze over Bay of Bengal. And then this is 2002, so this is very soon after I started at Goddard. We had this extreme smoke event that came from Canada and brought huge amounts of smoke. And I remember we could smell it, and it came all the way from Canada. So anyways, how do we do this? So what a satellite does is it measures, it measures in multiple channels, in this case, what we have. So it's measuring something that looks a lot like a picture, an RGB. It's also measuring in other wavelengths too. And so we're trying to quantify, we're trying to attribute how much of this is due to aerosol. And so what are satellites actually seeing? Well, they're not only seeing the atmosphere, they're seeing in the same field of view, they're seeing trees and water and grass and soil and then in the atmosphere itself, there's particles, there's gases, there's clouds. And so we're going to start with a little game here to describe what we see. So Pawan, please help us get together. So we'll grab some of the stuff.
Can you hear me? Okay, so what we are going to do now is try to actually mimic what is on the slide. And how many of you know how satellite works? When we say satellite make measurement of particles or gas, how many of you know what it make measurements of? Anyone? How many people use satellite data for anything in the, I know a lot of people are here from EPA, RTI, so you are involved in research and other things. Do you use satellite data for anything? Not only air quality, but for anything? Even looking picture of your house or anything. Do you do that? Okay. So in a layman language, satellite does take pictures, right? Because it's really high, 700-800 kilometer up, especially the type of satellite which we are talking here. So basically they take picture, but they are really advanced cameras in this space, right? They just do a lot more than taking pictures, right? So, but converting that picture into the information which we are using, which in case we are right now doing the particle pollution, right? We are trying to measure amount of particles in the atmosphere, right? So fundamentally what satellite does actually in this picture you can see here is there's a source of energy, sun, which transmit the light in different spectral bands, right? Different wavelengths, different colors, right? Red, green, blue. So those are different wavelengths. And as it passes through the atmospheres and the interact with the objects on the surface, it leaves their signature. It's just like if you put your, hold your bottles or anything, you put your fingerprints on that, right? It's same thing. As soon as that light interact with these things, it leaves their signature on it. And some of that portion of the light goes back to the space, and that's what the satellite is. And that light is measured by the satellite, right? Everybody's on with me so far? Okay, so what we're going to do in this game is we will just try to make it more interactive so that everybody gets the idea about what is going on here. So I will need some volunteer. I will need a person who can act as a sun, source of energy, just anyone. We need 7 or 8 volunteers, so don't worry about it. Okay, come on. Whoever wants to volunteer, come on over here. It's just a little fun game, okay? We need 7, 8 people. Oh my God, all women. Where are the guys? Okay, Rob, can you pass on one to each of these people? So we'll do a role play here. We'll have somebody playing trees, vegetation, somebody playing water, cloud, particles, and then we will need people who will play role of sun, and then I think leave it there. Okay.
Me and cloud.
Okay. Okay, we need one more person. You want? Okay.
Be a cloud.
Okay. So, Sun, can you come over here? And then all the classes, you go here, a little bit here, satellite over here. So this is satellite. Okay, is up in 700-800 kilometer. Sun is far millions of kilometers away. Light is coming from the sun. Can you? Yeah. Can you? Yeah. Okay. Can you hold these balls? Okay, you are cloud, particles. Okay, your vegetation. Here you go, cloud.
Make it look crazy up here.
I think I need to be pretty white.
I don't have all the colors.
Here, you should be Argentine.
You got it?
Yes, I'm good.
Yeah, good. Yeah, good. Okay, so what we are going to do is now, so sun has a source of light, all the rainbow colors, all the colors which light have all together. It will send that light towards the earth where you have water, clouds, vegetation, some aerosols, and then some desert land, right? And then here is the satellite. So sun will throw ball one by one to each class. And okay, now, yeah, for time being, you can keep it down. If you don't, the small balls, you can keep it down. So once each class receive the bundle of energy in form of all the wavelengths, in form of the beach ball here, the classes, the the objects will decide which wavelength of the light they will reflect. Okay, so now anybody, what is the fundamental principle? Why we see the water blue? Why we see the vegetation green? So, okay, I will ask, why do you think the water is blue? Okay, anybody else? Why do, means usually water is not blue, right, when we see it, right? Okay. Rob, why cloud is white? Okay. What about the vegetation? Okay. And what about aerosols particles? Yeah, I mean, they can reflect depending on what type of particles they are, right? Okay. And what about the sand or desert area? Yes, definitely. So you have three different wavelengths. Which one you think will be reflected more from the type of land you have on yours? Right? Okay. So the idea is basically each object or through which the wavelength or the incoming solar radiation is interacting, based on their property, they will absorb certain wavelength of light and they will reflect certain wavelength of light. Sometimes it's not that complete absorption and complete reflection. Sometimes some amount of red light will be absorbed, some amount will be reflected. And that's how we see different colors depending on their property. So now you make the decision which ball you have to throw. Just throw one ball towards the satellite, okay? Not all of them. If your property says that you have to reflect all the wavelength, then you can throw all the ball. And the satellite has to bring basically multiple cameras. Satellite usually have many cameras to detect the wavelength from each of those type of wavelength actually. Sometimes it detect all the wavelengths together, and then there are separation within the satellite system which separate them and make measurements. So we'll let satellite decide how he wants to handle that. Okay, so everybody got it? Okay, let's throw to water. Good. So why did you throw blue? Okay, you feel blue. That's good. Okay, now let's do the cloud. Okay. So white color is not fundamental primary color, right? When you mix all the colors, the three primary colors, it becomes white. So, and cloud has been known to reflect all the wavelength in the visible in the same with the same intensity. So that's why it appears white, and that's why you throw all three balls. Okay, now the next one. Ooh, good. So vegetation, it does reflect other wavelength as well, but most of the reflection comes in the green wavelengths. That's why it appears green, especially the leaf. There are other parts of vegetation which may reflect other wavelengths as well. So it's based on the chlorophyll content in those leaves. Okay, the next one. Okay, so particles. This is very tricky now because particles can have a different size, different shape, and different chemical composition. Now, based on all these three factors, they can interact with different wavelength differently. Most particle in our urban location which comes out from the automobiles or industry, they are like sulfate or nitrate type particles or carbonous particles, and they are very fine in size, right? PM 2.5 we have been talking about. And they mostly reflect actually most in the higher wavelength, which is red in RGB, red, green, blue, and then less in green and the blue. So depending on the particle's property, their relative contribution, their relative reflectance will change. Okay, so that is why we use, when Rob was showing that, we use many different channels. When satellite is designed, like for example, the MODIS, which was showing earlier the pictures, it has 36 different spectral channels. So it can make measurement in 36 different wavelengths. And that allow us to not only see how many particles are there, but to show up to some extent whether there is smoke or dust or urban pollution. Okay, next, the desert. Ooh, directly to the satellite. And that also happens. So that also happens. Okay, so you got it? Okay, great. So now, so this is just to, this is kind of end of the game. This is just to show how the satellite really works. It does not make direct measurement like purple air is sucking the air and going through doing at the surface. It's making measurement at 700-800 kilometers, taking pictures or making the measurement of that light. And now once that measurement is made by the satellite will transmit the data to the ground, and now it's our job to develop algorithm to extract the information which we want, which we can use it and which we can make sense. It's the same thing when Brendan was asking what is the temperature, right? So you have pretty good sense of that, but you don't probably have good sense of what is aerosol optical depth. But that's now our job to actually take that what is satellite has measured and extract that piece of information and provide in data form. Everybody got it? Question? Comments? Okay, give a big hand to everyone. Thank you very much. Thank you, guys. Yeah, I can collect that. Now, Rob will continue with his presentation.
A little bit more about the sausage that we do.
Thank you very much.
Oh, check that out. So we played our game. But I do want to say that things are just a little bit complicated, and that it's not just the, the individual light that from each of the different targets that comes to the satellite, but they also interact with each other, and of course clouds and everything else. So we do have to come up with an algorithm that makes some assumptions. We use those observations that we have. We have to come up with an algorithm that's what we call the retrieval, which we infer the properties of the particles we're looking at. And finally, we have to validate it. And so, yeah, a little bit about this. So this is just a little bit about the remote sensing process in another way that I just mentioned. We have observations, we have the theory and the assumptions, like the science and the physics and the optics behind it. You have to infer what you're after. And then finally, you have products that then people can use for whatever application that they are for. So I'm just going to give a little bit about a satellite. This began with MODIS. It actually began much earlier with much earlier sensors, but MODIS launched on 2 satellites. MODIS is a sensor launched on 2 satellites from NASA in 2000 and 2002. Was the first one that had this multispectral ability. So it actually has 36 bands, not just in the visible that we were playing the game with, visible wavelengths, but also near infrared, longer infrared. So it's got, it really spans the range. And so you can get a whole lot of information about both the atmosphere and the surface, over land, over ocean, over ice, over snow. At least that's the idea. And it basically, this is 1 day's worth of measurements, so it orbits every day, and it gets almost everywhere on the globe each day, but there are gaps. And so we do our best to work with that. And so we have different retrievals. I happen to be the PI, the lead of one of these algorithms that we call Dark Target, but there's many other algorithms as well from different groups that operate, maybe use different wavelengths, different ideas, and slightly different physics to work with, and maybe work better over one surface or another. But our job is to get optical depth over. This happens to be an image from 2001, which was related to a large, just regular old garden variety summer pollution case, but we had really large optical depths and very low, pretty low air quality over the DC area. And so that's what we're after. I have this movie. This thing has been up for 20 years, and what's fun is it's global, right? So now you can see. So on the left over here is active fires. So this sensor has the ability to look at fires using thermal signatures. But also here's our retrievals of aerosol optical depth. And you can kind of see in some places they're very heavily correlated with fires. But there's other stuff going on too. There's dust that comes off Africa. There's, of course, like I said, the fires and the biomass burning in the Amazon and over southern Africa. You have the huge pollution in East Asia and India. And you can see episodes now and then over the Southeast US, where some of it is fires, some of it is pollution. And so you can get a sense of this. So this is a 20-year time series that, and you can, I should have put the link on the web, but it's a movie you can go see. There's a site called Earth Observatory that has daily imagery and movies and everything from NASA sensors. So that's the 20-year time series, but 20 years is a long time for a satellite to be working up in space. So we are trying to work beyond MODIS and take our same algorithms and port them to new sensors. So there's an operational NOAA sensor called VIIRS that it will be in operation through the 2030s. And so we ported our algorithm and products to that. And then we are trying to work in the geostationary world as well, where you can take measurements over the same region, including the eastern US. So that's like GOES, which you got the patches from. I happen to be the recent GOES-R Deputy Project Scientist. So I have a new title at Goddard. Anyways, but remote sensing is not just satellites, there's other things too. And so all of this goes together. Airborne instruments, balloons, so we do have some remote sensing from airborne instruments as well. And of course, some of the low-level stuff too, including citizen science that we're working on here. So, all kinds of measurements from all different altitudes and all different kinds of platforms. And just a fun little movie on, so MODIS that I described is what we call polar orbiting, and it makes this kind of image every day as the Earth rotates. It continually stripes out an image. As opposed to geostationary on the right, where it's always over the equator, and you can see it's always facing the same part of the globe all the time. And so the next picture will kind of show you how that looks like in observation space. So a MODIS or a VIIRS is carving out the globe like this. It's of course not seeing daylight on the other side of the globe, so that's why it's only producing something that we can see. It is actually measuring at night too. It's measuring infrared, but it's measuring visible on the daylight side of the globe. And you can see the geo-orbit is seeing the same spot, but the sun is turning. So it's going from night to day, or day, morning to evening. And so this is how we're trying to look at aerosols and clouds and all other properties from space. And and the cool thing with the geo sensors is now you can do high temporal resolution measurements that we couldn't do before. So this is an example of some smoke in Brazil, and this is every 15 minutes near sunset or so, but I'll run it one more time. Oh, oops. I'll run it one more. I want to go back too. And, and you can really see how things move, how that smoke is moving and interacting with little clouds as well. And so that's actually a fundamental research interest that I have, is how these particles interact with clouds. So that's the thing. So, and you can kind of see with our old observations with MODIS, for example, you see twice a day. Those are the two red lines for, let's say, over here in North Carolina. But the new geos can see the whole day, and you can start to look at temporal, how things change during the day. So that's what we're doing. Here was our first attempt at retrievals from these sensors. And you can see there was a huge smoke event in Northwest US and Canada, as well as fires over Brazil. And the little eyeball in the middle is actually, unfortunately, we can't retrieve where there's sun glint facing us. So the mirror of the ocean is backing, and it's so bright that the satellite can't see what we're trying to see. At least we can't retrieve aerosol properties or with confidence. What? Too much noise, exactly. But you can sit here and look at these images forever. I can do that. But you can look. I think we'll share all these things later, so you can see them later on. But what is, of course, the problem that we have here is that, as I mentioned, that's what we call aerosol optical depth. It's the whole column. We are sensitive for these kind of sensors There are also other sensors that are helpful too, but from this kind of global measurement, we are sensitive only to the whole column. We can't tell really what's at the surface and differentiate between the surface and the above. And of course, what we're interested in here is what's going on at the surface, the PM2.5 part of it, so there it is in your face, but we can't see it, through the whole thing. And that's why we need these combination of satellites and surface measurements to work with. So this is in Pawan's paper that he talked about here for the California fires, but there was a movie associated with it too, which is from the first part, for the first deployment of this network. There were some sensors at the surface in LA, and this is a few days. Let's see, how do I play it again? This is a few days during October of 2017. You can kind of see satellites on the left and surface on the right, and they are correlated with each other, but not one-to-one. It's not like you always have an up in PM2.5 and an up in the satellite. The gradients are probably a little bit different. And the complicating thing is that aerosols have profiles. Like sometimes they're high up. They're not necessarily at the ground. You have long-range transport. You have dust. You have smoke that comes. I showed that picture before. Some of that smoke was coming a long way, far away, and it was not at the surface. Sometimes it came to the surface, but sometimes it stayed many, many kilometers, a couple miles up in the sky. And it's so the hard part is trying to train and trying to understand how do you get the surface portion out of the satellites. And so that's how we're interested in creating these networks of sensors. So let's go one more. So Pawan had made this picture before of, it's not this region, but it's in Asia, and looking at these huge fires and smoke. Here's some fires. This is not, this is not a quantitative assessment from the satellite, but based on some simple calculations, you can make a fairly decent estimate of what the air quality might be in terms of categorical from the satellite. So this is a movie of the sense. There's a bunch of sensors in Japan. These are not the same. I don't think these are actually, I don't know what kind of sensors they are. Do you know, Pawan? Okay, so these are all regulatory ones. Okay, so these are actually regulatory sensors in Japan, but you can see the color scale pretty much matches what the satellite. If you make a decent model and decent assumptions, you can get a reasonable guess from the satellite at what's at the ground. And of course, we're trying to make that better. So I think that's the last slide. Oh no, I got one more slide. This is again, not quantitative in a way, but it's, kind of gives you, if you take all the different sensors we have access to right now, or at least 6 of them, which is a geostationary called goes east, a geostationary goes west. These are operational NOAA weather satellites. Himawari is a Japanese satellite that is very, very, that has an imager that's it's basically the same as the GOES imagers. And then the 3 on the right are the 2 MODIS images and the VIIRS. And you can kind of see, as I'll just play this movie again, how as you rotate the globe around, you get the kind of the global coverage every 30 minutes or so. And soon there'll be a European one in the middle that'll then really be able to cover the whole globe. And so, of course, we're very interested in trying to make that global understanding of aerosols and surface pollution globally. And so, again, we just, Brandon showed a map like this, but just this was from, picking one random day a while back from the Purple Air Network over the US. And, the question is, how does this kind of gradient at the surface, or how, does the gradient from the satellite match pretty well with the surface? And how do you get from the satellite data and the observations and the retrievals to get to something that looks like this? So that's what I have. And now the next would be Pawan going over some details on how to get and use and interact with some of the satellite data. So any questions for now as we are changing, please ask.
How many of you wants to really see the satellite data by yourself on the computer?
Yay, good, excellent.
Phone or computer on?